All right, thanks. Okay, so just to sanity check, I'm not wrong that this was supposed to start 3 minutes ago, right? All right, we're gonna have to get started. We've got a ton of stuff to jam into the hour and a half time we have. So find your places, sign the blue sheets. They're circulating from either side here. Welcome everyone. This is Maprg, the Measurement and Analysis for Protocols Research Group. I'm Dave Plonka. My co-chair is Miria Kulwin, who I'll expect to be here any minute. And this is the IPR statement for the IETF and the note well. And does anyone know how to fix that? Thanks. Yeah, when I was using the clicker, it's just advancing a part of the slide each time. All right, thanks. All right. So what we have on deck for today is well, here's the links to the things, everything Maprg. If you've not been to Maprg before, it's the Measurement and Analysis for Protocols Research Group. What we do is do measurements that inform the engineering or operation of IETF protocols. So everything you see here should be attached to some IETF protocol or the operation of it. We have a mailing list. Today's slides are up at that link. There's the Etherpad, the audio, the Meet Echo, the Jabber Room, all linked there. So the way we run Maprg is we put out a call for contributions. This time we did the same thing. On January 28th, we put out a call for contributions for presentations that have measurement results here in Maprg, and we received about 10 proposed contributions. A couple of them are out of scope. 7 of them were invited to present here today, of which I think you'll see 6. And because one of them was presented a day or two ago at the Quick Working Group. Thanks for the proposals. We got some really strong stuff. Unfortunately, this time, because of the way they changed the week around and had the free time during Wednesday, we couldn't get a 2-hour time slot, so we're in an hour and a half. So I think it'll go pretty quick. One of the things we do in Maprg, if you have a project that has a tool or your results aren't particularly mature yet, or you just want to tell something about an upcoming measurement conference or symposium, we'll run ads for you, and you'll see some of those here. So the tail end of the intro slides will be those ads. The other thing that we did new this time was MAP participated in the hackathon. So we had a Measurement and Analysis for Protocols table at the hackathon, and we had, I think, 6 of us at the table. And we'll give a short rundown on what happened there. But basically, we did the call for participants and projects there. We had 3 projects there, and 2 people responded in advance. 2 more showed up there, and with Miri and I, that was the 6 of us that spent Saturday and Sunday preparing content for for today. So the agenda for today is we'll go through this intro and overview, and then I'll give a rundown on what happened at the hackathon. Then Olaf Fitton is going to come up and give what we call a heads up talk, where we give you a short amount of time to introduce people to a project that you want the community to know about. And then we'll go into our longer measurement results presentations proper, which will have five of them in a row there, which is, well, we'll just go up one at a time. And then lastly, if there's time remaining, we'll invite Sherry from Google to come up and do the quick presentation. Otherwise, we'll just send you the link to the presentation that you did in the quick working group. As for advertisements, Ian Learmonth it has a draft about safe internet measurements, and it's certainly pertinent to this group. It's about what would be essentially like best current practices for how you would do measurements in the first place, and then perhaps also how you would catalog the results and what sort of things should and shouldn't be in those results. So there's a link to that draft there. Please review it, contribute to help Ian with that. One of the proposed presentations for today that is just in an early state, and we asked Luke to come back when he had some measurement results, is this project. It sounds like he's doing some really neat stuff with line rate up to hundreds of gigabits per second in packet capture. And so Luke's got his email address there. If you're interested in that project or that software, get in touch with Luke. The Advanced Networks Research Workshop for next year, the dates have been set. So let students and potential researchers that would bring work there, let them know about that. You can find it on the IETF website, and it'll be in this slide set. There's a quick interoperability and performance workshop coming up next year. The dates are here as well. That's the second venue for that kind of work. After that, then we have here's Miria.
Sorry.
That's all right. I've done this before.
I'm sure you're doing a great job.
So, and then we also have the dates up for the Internet Measurement Workshop. Very often we get to scoop the Internet Measurement Workshop by finding out what they accepted and presenting it in the summertime before them. So certainly one of my favorite venues. That's up. Also, the Internet Measurement Workshop is running a shadow PC again. So especially if you're a graduate student and you want to learn how to be on a PC, they'll run it in parallel with the regular reviews. Really neat experience, and of course fascinating when they pick different things than the real PC would pick. So get involved in that for you or your students if you have them. And that's the end of the advertisements. Could you switch to the next slide? Is that the next tab there? Sure. Okay, so let's see. I'm going to spend maybe 5 or 8 minutes going through what we did at the hackathon. So this was this past Saturday and Sunday, and so the project that I proposed was to work on privacy and security issues in IPv6 deployment. If you were at Maprg last meeting, Tobias Fiebig presented a proposal about we're exploring the way that V6 deployments are being put out in the world today and what we can discover that we think might be privacy sensitive or security sensitive to collect it as a set of measurement results and perhaps give it back to the V6 IETF community to say, is there something that should be different in terms of how the deployments are going there? So we're meaning to write an internet draft, and it would be probably the first one from Maprg reporting that set of measurements. And Oliver Gasser from TU Munich offered to come and work on this with me. So when we first conceived of Maprg, one of the things that Miri and I had as a goal was, could we get these private measurements that sometimes happen in industry where they can't disclose the details because it might be about customers or users on the internet? Could we take some of those private measurements and work together with people in Maprg in conversations and then digest the results and come up with some sort of summary results? So that's what Oliver and I gave ourselves as a goal. We would take his IPv6 survey studies from TU Munich and some of my studies from Inside Akamai and compare apples to apples and use the same tools to analyze them and try to produce a combined result that's more complete than either of us could offer you on our own. So what did we get done at the hackathon? Well, we considered what would be best current practice for privacy and security in hit lists. Right now, the IPv6 internet is largely surveyed based on seed addresses or hit lists that you use to do trace routes or reachability tests. And there's a link there to the TU Munich hit list, which was introduced in IMC last year. So a nice IMC paper about how they developed the V6 hit list and how they maintain it. And then we updated and released a couple analysis tools that I've used over some years to do V6 analyses. And so we're taking essentially what we think is the largest publicly known data set of IPv6 topology and reachability measurements, and as far as I know, again, the largest private one from what I do inside Akamai, and bring them together. So what did we learn? Well, the first thing we learned is between our two sets, just accidentally doing these topology and reachability studies, we found 1.2 million EUI64 addressed IPv6 routers. So these are routers that we know the manufacturer of ostensibly. Many of them are reachable on the internet, and we think this could potentially present a vulnerability in the V6 internet if any of these classes of devices are known to have weaknesses. The discovery of these was completely accidental. We were doing a topology study to discover the core of the V6 internet. He was doing a reachability study, and then we decided as a side effect, there were these router addresses in there. We also found that the public data set, the results that TU Munich prepared, and our set inside, they were focused on different parts of the V6 internet, again, sort of accidentally, so that the results were complementary. And you know, something like 40% came from one of the set and 60% came from the other. Another thing that was surprising that we found is in one of the studies, I was using a more than a year-old IPv6 hit list, and we found it discovered more results sometimes than the current hit list. So you can imagine these hit lists are curated over time, and you have to just make decisions about what do you add and remove from them. And some addresses, some seed addresses, had been culled from the hit list in the last year, and it turned out those were actually useful to find more of these V6 routers of interest. And then, so I'm gonna go through quickly a couple of the summary results. But basically, the middle column here is a device count, and this is EUI64 numbered devices that have IEEE MAC addresses embedded in them in various ASNs. So we found an ASN that had something like 300,000 of those at the top there. There were 571 unique ASNs that we found EUI64 numbered V6 routers in their deployment. We found of the top 10 vendors, we found 235 unique vendors, but the top 10 you can see here make up something like 99% of it. So there are particular brands of equipment that networks are choosing to deploy in their V6 deployments. 235 different unique vendors in total. And what we decided to do, so I said that there's privacy concerns with the data. So what Oliver and I did is we anonymized the ASNs here and we anonymized the vendors. So I took a bunch of fictitious company names from movies and television, like Wonka and Ollivander's Wand Shop. Those are the manufacturers of the devices. And then we made classes of them where we paired up the ASN and that particular brand of equipment. So here, 23.5% of the EUI64 numbered V6 routers were manufactured by Wonka Industries and were in ASA. And what you can see here is, for instance, here's two different ASNs that use the same ostensibly popular brand. In this case, we've substituted Acme Corp brand equipment in there, and that represented some 20+% of it. And then you can see that same brand is used by ASG down there as well. So just trying to give you an idea of what, and then we also see things like, here's an AS that uses, has a high population of two different brands of this equipment. Now, there's many of these brands, so let's try to dive in and visually in a couple of these. So what Oliver did is, over about the past 6 months, he did a time series plot here of the 5 ASNs in these 5 different colors, again anonymized, but this is on the vertical axis, the number of devices that were numbered using EUI64 addresses. And the top of it is 500,000 there. So this blue line at the top saying over the last half a year there was a decrease in the number of EUI64 number routers there. But and we saw some anomalies, like for instance where a number of ASNs the number seemed to drop, and unfortunately we found that that's just an artifact of the way the measurements were done. What we were seeing instead is over the last half year there's a number of ASNs that the number of EUI64 numbered routers, which is a legacy addressing technique, they're actually increasing. So we think that current V6 deployments are numbering routers this way, and a lot of them are customer premise equipment, so there might be potentially PII concerns there. Another way we visualized it is on the horizontal axis here I have the top 20 ASNs that had the most UI64 numbered routers discovered from the this private Akamai data set. And what I want to show you is just a couple of the modes of results we see here. So here, the green line there at about 20,000 is the number of target addresses that we traced towards in these networks. And you can think of these as web clients that touch, for instance, Akamai hosted properties. And by tracing towards 20,000 hosts, we discovered 110,000 UI64 numbered routers. That's the only data point in that particular ASN where you trace only to 20,000 endpoints, but you discover more routers. Well, what does that mean? It means that they must be using UI64 when they're numbering things in the distribution layer of their network, that we see multiple UI64 hops on a path towards a web client. The other thing we see is here, where the red is the number of UI64 numbered routers. The red line is the number of UI64 routers that we discovered. The green is the number of addresses that we probed towards. Well, here they matched up exactly. That means when we trace towards a client in that network, we pick up one UI64 numbered router, ostensibly the one that's in the customer premise. And then there's also these bimodal results where we scan less than 10, where we scan towards about 40,000 and we call about 10,000 UI64 routers. So there's quite a distance. Not every path towards one of the clients seems to have that kind of numbered router. But then there's other ones where the red and the green are really close together. So we almost harvest in survey one UI64 numbered router for every target we trace towards. And then, so those are basically the early results we got from this V6 security and privacy study. And basically what we're finding is that because things were all over the place with different ASNs, we really need to do a more focused study that tries to figure out how many of these are there. They're really just being accidentally discovered. So we're going to set ourselves up for some follow-on work, and we'll bring that to Maprg when we have it. Another project was Al Morton did a project at the same table, where I'll just leave the slide here, but you can contact him about what he's doing. It's basically new ways to do performance measurements at the high line rates that are in the last mile in modern internet. And then Miria and Ian did a Pathfinder survey as well. So we set ourselves up with wired internet access at the table, and you can do some active measurements if you can. So if I come to the meeting in Montreal, I would love to have another session for MAP for the hackathon. So get in touch with us if you're interested in doing that as well. And those are the folks that were at the hackathon. So we're going to run late, so we're going to switch into the next presentations, and then if we have some time at the end, you can ask any and all things about the ones along the way. Olav, where are you?
Thank you. Well, I've been using the internet for a while. You can see my hair. My hair is white, and I had all these sessions. My web browser freezes, my video session hangs, my companions fell out on the video, and I had always thought, well, it's my shitty operating system. So I rebooted my PC. I restarted my browser and whatever. But then I had a nudge that there could be problems in the network. So I started this project 10 years ago to do let's say, a global measurement of the inter-domain dependability. And we have just collected a few sites. These are mostly research networks over the world at universities and so on. And the measurement was quite simple. We just sent 100 packets a second between UDP packets. And then we analyzed the results afterwards to see all the gaps in receiving the packets. And we developed some metrics to try to understand what happens each time you lose a packet. Like what are the queues at the moment when you lose a packet? Well, just one more thing. Initially, we set this up as a research project, and we had people at the university that run a couple of PhDs and some MSc thesis on this. And I was helping out one of the MSCs one day, and I discovered that the sheer engineering numbers of outages was huge. I discovered that each week there was around 1,000 outages in this mesh of 10 nodes. We lost, let's say, in the order of hours every week in time just waiting for routing or anything to come back up. So we started to investigate in, let's say, each event, and we found quickly some short engineering measures to solve some of the problems. It turned to be mostly these kind of problems related to BGP boundary crossings. So we had the passive mode BGP to our customers that resulted in 2 minutes outage when you had a redundant connection. You had misdone router upgrades. When we started, evading the routes from the routers before we boot them, you don't see any outages. So, and we also saw that a sheer fiber cut or instability costed 79 seconds. And that is probably due to BGP or whatever, the router rewriting the forwarding table with the full BGP routing stack. So you really can't afford even a small change in the routing table. So there are mitigations to that. It's for example, the PIC, the protocol independent convergence thing could update routes faster, but definitely we can't afford a 1 minute outage on a routing change. So as you can see here, here's a distribution of the outages, and there are a lot of outages in the area of 50 milliseconds or less, and that's probably, let's say, random early discards or whatever. So that's probably that's a functional network, so we shouldn't care too much about them. But you can see that the violet figure shows that the most of the time goes to the bigger outages, which is in the order of 50 seconds or more, so minutes. And that is, to me, looks like could be, let's say, BDP-related, configuration-related problems. So I guess we need to do, all of us, do better BGP tuning and configuration. We need to have a faster, better hardware for PIC or stuff like that, faster convergence. Yeah, I'm working. So as you can see, I have a limited number of nodes, and if anyone are interested to join or help this project with, let's say, brain power and also some hardware, I just need a Unix account. So let me know. And I hope there's a lot of stuff to be discovered here about how the internet actually behaves. Thank you.
Thanks, Olav. Jörg, are you? So next up we have Jörg Deutschmann presenting about satellite internet performance measurements.
Yeah, hello everybody. My name is Jörg Deutschmann. This is my first talk at an IETF meeting. Thank you. And the topic is satellite internet, which was also on the agenda at the previous Maprg. So what's it about? It's about geostationary satellites. We have high propagation delays, so RTTs above 600 milliseconds. And that's why we deploy performance enhancement proxies to do split TCP. Unfortunately, with encrypted transport layer headers, we cannot use split TCP anymore. And at the previous Maprg, Nicola Kuhn already presented the principal problem of this. He compared HTTP2 to QUIC. And our findings complement his results. We agree with him. And yeah, let's have a look at this. So there are 3 major operators across Europe. Sadly, none of them has IPv6 support, which is not that important for our performance measurements, but I still wanted to have it mentioned. So what we did is black box testing of all three operators with very simple active measurements, which were one-way UDP delays, bulk data transfer, which I'm not going to show here, and page load times with common web protocols. Okay, let's start with the one-way UDP delays. We send 1 byte UDP packets in 1 second intervals. We use the same physical host for sending and receiving packets, which simplifies clock synchronization. And of course, we have the impact of the backbone network, which we assume to be neglectable for now. These are the results. The delays in the return link are in general higher than in the forward link. Operator C shows very stable delays, whereas operator A and B suffer from UDP jitter. We have no insight into the system, so the reason might be some layer 2 channel access mechanisms or some impact in the access network of the operator. So, but let's keep these delays in mind. Next are the page load times. So we had a look at different HTTP flavors. We considered Google Quick with 2 different implementations. For all tests, we also set up an OpenVPN UDP tunnel, which allows us to disable the performance enhancement proxies. And we designed 2 static websites, a small one with a total size of 1.4 megabyte and a large one with a total size of 10 megabyte. Our HTTP server did not have any features like server push or stream prioritization. So here are the results, and as expected, the TCP connections optimized by the PEP provide the lowest page load times, in contrast to the ones going through the UDP tunnel. Again, for all experiments, operator C shows the most stable results, and it even gets more rigorous when looking at Quick. So let's have a look at Chromium Quick. With Chromium Quick, operator A and B suffer from, I would say, insanely large variations. Whereas Chromium Quick with operator C works quite well, even better than the TCP connections going through the VPN tunnel. But still, if you compare HTTP2 to Chromium Quick for operator C, you see that the page load time is roughly twice. And this is exactly the same result which we also saw at the previous Maprg. For Quick Go, the variation is not that high, but also the total page load time for when using operator C is not that good. For the large website, the key messages are all the same. Therefore, I won't go into detail here. But I think it's still remarkable that the order of magnitude for some experiments is like really large. Okay, as one of the last slides, I want to show you some work in progress. In the meantime, we have moved to IETF draft 17. We're requesting a 1 megabyte object within a single stream. And each figure shows like 10 traces, plotted as gray, and the black line is 1 trace picked by hand. So the first row is our reference, HTTP2 optimized by PEPs. You can see that the object is more or less received at line rate. In the second row, you see NG-TCP. Again, the operators from left to right are ABC like before. So with NG-TCP, you see some retransmission bursts, which is not the case for the third row, which is Quickly. Quickly works quite well for operator C, but somehow fails completely with operator B. We do not have an explanation for this yet. And I have to emphasize that, of course, all the Quick implementations are work in progress, and they're all great. So this is not meant to rate the implementations. It's just first impression what awaits us with QUIC over satellite. And these results match the previous results and also match the results from the previous Maprg meeting. So as a conclusion, I would say TCP traffic benefits from PEPs, no surprise. The performance rise among operators, also no surprise. However, the performance differences were, at least for me, surprisingly large. And I think it is an indication that some operators have not tuned their network for QUIC yet. And there seems to be a correlation with the UDP delay variation. If I had one wish, it would be that in future performance studies, not only high bandwidth delay product links are considered, but explicitly satellite links. And as a future work, I would say a lot. That's it.
All right, thanks, Jörg. And you helped us get back on schedule. Thank you. So we have time for a couple of questions.
I'll shout. So these are measured data, right? And can you say something about the services that, when you talk about different operators, they have a wide range of services, access bandwidth, that sort of thing. Is that in the paper? Or can you describe, like, are they comparable between operators that you see? Are the locations,
Yeah, it's described more detail in the paper. So roughly, we have used. The question was like, what was the setup of the operators like? Did we, were this comparable setups? And the answer is we have chosen similar tariffs for the operator. So
sorry, say that again. You chose what?
Similar tariffs. So like similar products. The download data rates were all between 20 and 30 megabit per second. And so I would say they are comparable.
Were they dedicated channels or was there sharing?
Of course, it's a wireless channel, so wireless cellular network with multiple users. So we have no insight how the layer 2 channel access is done by the operator, which is of course important.
Sorry, you said a cellular network? I thought it was satellite network.
Satellite network,
Okay.
A wireless network with multiple users.
Okay.
So we have no idea how the layer 2 mechanisms work. And this might, of course, be a good explanation for the differences.
Praveen, Microsoft. Well, one question I had was, so is there any way to do the TCP measurement without going through the PEP, like without split TCP? Is there a way to force that and measure that?
Not really, not as an end user, I would say. That's why we use the OpenVPN tunnels. Of course, the OpenVPN tunnels on UDP suffer from the UDP delays.
Yeah,
so
right. So there's no way to measure TCP without split TCP?
Not for us.
Giovanni Saidian, thanks for the presentation. Very interesting. From the measurements point of view, I usually don't do satellite measurements because I don't have any access to a satellite network. Do you know if there's any public measurement platforms? If RIPE Atlas, for example, is there any probes in Atlas that actually have a satellite connection, or any operators in the room, if it's not the case, would like to host one?
At least we have a RIPE probe at our satellite links.
So, and I can use that from. Oh, sure. Thanks. That's great. Thanks.
What's the probe ID?
Probe ID.
I don't know by heart.
All right. Can you send to the list, the Maprg list?
Sure.
All right. Is there a tag satellite?
Oh.
Of course, we disabled the probe during the measurement, so it was offline for quite some time.
Thanks.
Gabriel Montenegro. So you mentioned so there were some quick and different implementations of quick testing. There's also been some work, and I know Nicola Kuhn is involved in that work to make quick, quote unquote, aware of satellite links. Increasing BDP or increasing RTC or whatever. Did you implement any of those mechanisms? Experiment with those at all, or is it just pure quick off-the-shelf?
No, we took it off the shelf. And
Got it.
of course,
Okay.
that's an interesting question. What can we do for satellite links? I think that was already discussed last time. Yesterday there was a interesting side meeting about localized optimization of path segments, which might help to make the satellite link more robust. But also you have to touch the end, the implementation parameters for quick, like large initial window and so on.
Okay. Thanks.
Thank you.
Thanks a lot, Jörg. So next up, we have Pavel Feremsky and Oliver Goss are going to talk about the DNS Observatory. We're going to switch to this presentation.
Okay, no problem.
Yes, so hi, my name is Pavel, this is Oliver. We are here to present you a new research project of Farsight Security, DNS Observatory. The goal is to gain insight into the global DNS space using a kind of a telescope, and eventually to give access to the data to researchers, because we found that it's not so often that researchers have access to such data. To begin with, we start by analyzing a large stream of passive DNS observations from recursive resolvers around the world. That is, we analyze the traffic between the recursive resolvers to authoritative name servers. That is what happens above the recursive resolvers. For those of you who have heard about Farsight Security DNSDB, that's completely new machinery. And we track only the big guys, the top N objects. For that research, we focus on top 10,000 name servers, but also other objects I will describe. And we focus on the data collected in the first 3 months of this year. That is more than 1 trillion cache misses. And we are just starting. We just want to preview the data and ask you what would you like to see in the final work. So as to the galaxies we track using this telescope, the tracked DNS objects, we aggregate the DNS traffic, that is the query response traffic, by few kinds of keys. Foremost, the server IP address, the IP address of the authoritative name server, but also effective TLDs, SLDs, FQDNs, Q types, but also either the v4 or v6 address we have seen in DNS responses to A, quad A, or any queries. Every minute we dump a list of top 10,000 objects ranked by the number of queries we have seen, and we aggregate these minutely files into larger files like 1 hourly files, daily and monthly, and so on. Each tracked object, for instance, each authoritative name server or each TLD, is characterized using 30 features of few kinds. First of all, counters, like the number of DNSSEC signed responses we have seen from a particular name server. Also cardinality estimates, which from us is the hyperlog algorithm, like the number of distinct FQDNs we have seen from a particular SLD. And histogram estimates, which allows us to get median response delay, including the quartiles, the top 3 TTLs we have seen for a particular record, or all records we have seen in responses, and so on. So the very first result we'd like to show you, this graph presents you the result for top 10,000 name servers seen during the first quartile. Is the distribution of traffic. On the x-axis, you see the server rank, so the big guys are on the left. This is where the root name servers and TLD name servers live. On the right-hand side, you are more likely to find zone authorities for SLDs and so on. And we found that 60% of the queries we have analyzed are handled by just top 1,000 name servers. And when you filter by the response code, for instance, NX domain, which is visible in the red curve, and traffic is more shifted to the left, which kind of tells a story that more popular name servers are the first line of defense from the garbage traffic. I mean, queries for non-existent domains. The root servers really get a lot of garbage queries, whereas you are more likely to find the answer to the right-hand side to less popular name servers. We also analyzed how DNS traffic from recursive resolvers to authoritative name servers are distributed around names of networks. That is, we aggregate by name in the AS. We put the names aside because there is no particular reason to blame these organizations for. We would rather want to ask question, is DNS really distributed? I mean, just to start discussion and just to start research. We found that just 8 organizations handle 53% of DNS traffic we analyzed. Here we show the median response delay. So on the x-axis, you now see the response delay, y-axis is the CDF. Although 50% of the servers, server IPs we have analyzed responded in less than 25 milliseconds, but still 1/5 needed more than 100 milliseconds to respond, which suggests many recursives need to cross an ocean to get to a zone authority. We, of course, disregard the health of the name server, but, well, there's clearly space for improvement, and it may motivate replicating some zones closer to recursive resolvers, obviously. And now, time for Oliver.
All right. Okay, so we also would like to point out the DNS Observatory can identify significant events. And what we see here is the second-level domain of a large hardware vendor in the .com zone, which basically reduced the TTL of the resource record to 0, which you can see on the 19th of March, which is the blue line, basically goes down to 0. And what happens as a result is the green and the red lines start increasing. So the traffic volume and also the response delay starts increasing as a result, because the authoritative name server of this hardware vendor gets hammered with queries. This hardware vendor then also came up with the interesting idea to add more servers to cope with this problem. But finally, they fixed the problem by setting the TTL back to a sane level, which then in turn results in decreasing values for response delay as well as traffic volume. On this slide, we show the introduction of a new GTLD. And what you see here is the green curve shows the traffic volume again, which shows significant events when, for example, the GTLD was made publicly, and you could buy TLDs. You could buy domains under this TLD. And what we also see is the slight increase in registered domain, and also the number of servers which are authoritative within this GTLD. What's to note, however, is that the overall traffic is not significantly increasing over time. This means that no, let's say, large service yet is operating with under this new GTLD. Now to another interesting effect that we saw, namely the combination of the happy eyeballs algorithm with negative caching, which leads to some interesting effects. So happy eyeballs, as you all know, is if you have IPv6 connectivity as well as IPv4, you will send A and quad A queries to resolve an FQDN. And negative caching, on the other hand, allows you to cache negative responses, or allows the recursive resolver to cache negative responses in order not to hammer the authoritative all the time. So we found two interesting effects here. The first one being that some ISP resolvers do not cache empty quad A responses at all, which of course leads to a lot of unnecessary quad A queries. And the second one being that some FQDNs have a very short negative caching TTL, which then results in a large quad A query volume. And we're going to into some details in this graph. So on the x-axis, you see the top 200 FQDNs ranked by traffic, and on the y-axis, you see the share of empty quad A responses for each of these specific FQDN. So the higher these spikes are, the more empty responses for quad A records you get. And we want to show you three examples here. So the first one is a CDN, which is used for operating system updates, which has a record TTL of 1 hour, but a negative caching TTL of only 15 minutes. And this results in almost 90% of all responses being quad-ANO data. The second example that we look at are actually two specific FQDNs which belong to a large ad serving network, where we see a regular TTL of 5 minutes, but a negative caching TTL of only 1 minute, which then again results in two-thirds of all responses being empty quad-A responses. And the last one that I want to show you is two specific FQDNs again, but this time for an OS time service. And here we have the most drastic effect, I would say. So we have a regular TTL of 15 minutes, but the negative caching TTL, which is 60 times lower, namely 15 seconds only, which results in 90% of all responses being quad-ANO data. So these examples show you that the effect that if you have the happy eyeballs algorithm in play with short negative caching TTLs can lead to a large number of basically, let's say, useless queries. Okay.
So you have probably heard of these DNS hijacking attacks, right? If not, please download these slides and click on these links. The short story is that DNSSEC and RPKI properly deployed should make these attacks much more difficult, and this is why we analyze DNSSEC and RPKI support in the top 10,000 name servers on the internet. Let's start with the red line, which is DNSSEC support. I mean, percentage of DNS responses with DNSSEC signed DNSSEC signatures. And in order to make this plot sane, we represent servers by averages for groups of 100 servers that are adjacent on that list, because otherwise you would see 10,000 points and that would be unreadable. So the red circle shows you where DNSSEC is most likely to be deployed. I mean, for the most popular guys, that is usually the root name servers and TLDs, which is, I think, common knowledge nowadays. However, when you look at the rest of the guys, it's not so well. And so when you measure the adoption by server IP, it's just 4%, but when you measure by traffic, it's 16%, which kind of aligns with the APNIC stats, which are linked below. For RPKI, for some reason, the guys in the middle are more likely to sit in prefixes signed using RPKI. We also analyzed, well, what if a server is secured using DNSSEC or RPKI? I mean, either of the two or both, and that's the black line. So intuitively, the distance between the blue and the black tells you how these two techniques complement each other, if the distance is high or if they are deployed at the same time.
Sorry, clarification question here.
Yeah.
DNSSEC or RPKI, I mean, that's the set union that you're taking here.
Yes.
You didn't look at intersection.
Yes, that's the union, not the intersection. So when you average by server IPs, 44%, and by the traffic, 49%. So I think for now that's it. Just to summarize, DNS Observatory is a new project, provides aggregated view in time, and we found that the infrastructure might need more work in performance security. As I said, we are just starting, and we'd like to hear your feedback. Foremost, what evaluation would you like to see in our final work? What did we do well or not? And if you're interested in playing with the data, please do drop us an email. We are generally open to share the data with researchers. Thank you.
All right, thanks, guys. We're just barely on schedule, so let's take the questions and comments that are at the mic right now, and then we'll move on to the next. So, no.
I'm trying to make it quick. Alex Mayover from Leak.at. Great work. What I would really like to see is a function that actually allows me to estimate the traffic change depending on a TTL change. So that would be, I suppose it's something like this. So yeah, if you can get that function out of the data that you have, and that would be a great estimator to recommend to customers. Yeah. Yes. And also to compensate for measurements between domains with different TTLs. Yeah.
Yes, exactly. Thank you very much. That's already planned. Thank you.
Hello, Peter van der Wijk, Power DNS. You mentioned that the happy eyeballs cause a lot of extra queries that result in no data. Right now in the DNS, the negative TTL is used both for no data and NX domain. Would you agree that it might make sense if servers split those numbers?
Boy, okay. Yes.
Okay.
Does it answer your question?
Sorry, what?
Does it answer your question?
Yes.
Yeah.
Okay, that was the fastest questions ever. Anyone last question?
I'll bring mine back because it's a little bit long and we might have to take it offline.
You have to say your name as well.
Oh, hi, Brian Trammell. Yeah, so I'm a little confused. I would be interested to see the intersection as well as the union, because I mean, like, so there's an understanding that like one or the other is enough, but there are a few attacks where both would be really useful to see. So I suspect that number is a little bit lower, and I'd like to see it. Thanks.
Sure.
Could you go back to the first Grafana black graph? And I'm Wes Hardiker, ISI.
Yes.
So I don't understand your conclusion from this one, because the response delay doesn't go up while the DNS traffic goes up, and you were, I mean, there's a shift between the green and the red line, and your statement sounded like a conclusion that they were aligned.
So, yes. So you're right. So it doesn't go up in parallel. That's what your question is about. Okay. Yes.
Well, you stated that dropping the TTL increased the delay, and it didn't for like the first day, as far as I can tell.
It didn't for the first day. That's correct. So as we also mentioned, so this is preliminary work. We don't have all the knowledge that plays into the DNS. The DNS is a very complex system, as you all know. It could also play in that the people at this company added new servers, and those servers were maybe configured strangely. They could be very low performance servers, so we don't know that. So we don't know all the details, but of course we will investigate closer. Thank you.
All right, thank you.
Very quick.
Oh yeah, so this response delay in this graph, you're actually measuring traffic from resolver to authoritative, right? So I don't think it would be influenced by TTL, because if there would be in the cache, there would be no queries to start with. You know what I mean? If it's in a cache, you're not going to see the query coming from the resolver to the authoritative. The client's going to get an answer, right? You're measuring the response time from resolver to authoritative. What I'm trying to say is that the TTL would not influence the RTT if you're measuring resolver to authoritative.
Yes, so we are assuming that what actually made the response delay higher was rate of the traffic, not the TTL, because TTL of 0 increases traffic, and we assume that it was so high that the response delay went up. However, okay. And anyway, the point of the Grafana plots is rather to show that we have software for finding the trends in automatic way, not really to drill down into these problems, because it's some preliminary work.
All right. But thanks. Very interesting work.
Thank you.
Oh, thanks so much, guys. So next up we have Jason Sanchez talking to us about EDNS compliance status of resolvers.
And I believe you're a first timer, so welcome.
Yeah, this is my first IETF. Thanks for giving me the opportunity to present here. My name is Jason Sanchez. I'm a master's student from the University of Chile in the electrical engineering department. And I'm going to present the EDNS compliance status in different resolvers before the DNS flag day and after DNS flag day. Well, some background first. What is EDNS? Are the extension mechanisms to deploy new features in the DNS protocol. What kind of features? Extra data space for additional flags and also response codes. Also to send the message larger than 512 bytes, and among other features. What is the problem with EDNS? There is some, in the operational world, there is some workaround, as you know. And also there is a poorly firewall rules that block invalid traffic. And some authoritative servers block the response or answer with a wrong packet. What that means, the resolvers have to send again the query or wait for a timeout, and all this is by the bad implementations of DNS that not following the standards. The solution was provided by the DNS provider, the most common providers around the world. This day is to remove all the workarounds, was the 1st of February of this year. And I'm going to show you some results before the status, before the DNS flag day and after the DS flag day. Okay, I'm going to show you the DNS status of 19,061 resolvers. We developed an algorithm to test this in 4 stages. This was made by Dig tool and also a tool developed by Shimon Hyuk called PyDig. PyDig is a tool when you can send some option codes to test the different extensions. Each test was performed 3 times before the DNS flag day and 2 times after the DNS flag day to smooth the network failures, like timeout and others. The test number 1 and second, some of the tests in number 1 and second stage is based on the DNS updraft, a common operational problems in DNS servers that is at this moment in an advanced version. The first stage would get some information about the DNS version of the servers. Also, we test the eDNS support. This is the results of the server version. The most common is the bind implementation. Also, we can see here the eDNS hour. This is the command made by Dig. You can see that the most common response codes defined by the RFC 10 and 35. You can see that the most common response code here is no error R code. Also, we can see that the op code, according to the draft, the most they recommend that we have to see the option code in the additional section and the eDNS version number 0 in the answer. According to the algorithm classification, we can see that the most of the resolvers has a compliance with the eDNS version 0, but not complete. Is due to, for instance, we don't see the option code in the additional section. But also we can see that almost 9,000 resolvers has a complete compliance with the draft. Also, we can see the unreachable servers by timeout here. In the second stage, we can see the test for the eDNS version number 1, and also the test basic text based on DNSSEC. The first test here was eDNS number 1. We expected a bad version according to the draft, and also we expect an option code in the additional section. And the version number 0. Not all of the resolvers are according to the draft, as you can see. Here, the bad version, only 3,500 resolver response according to the draft. Also, we test the DNSSEC. This is a simple command to send here, but not at all of the resolvers has the flag DO, DNSSEC OK. And also we expect this flag if the RR-SIG are in the answer. This is the classification of the algorithm that we developed. Almost 10,000 has the response with the DO number 1 flag, and almost 4,000 resolvers has the no-do flag here. The third stage was to test the different extensions. I'm going to present 2 of that for the time. One of these is the chain query in DNS. That is our experimental RFC. Chain query is to deploy the DNSSEC client validation, and you can test by the PyDig tool. We expect here no error code and also another flags. This is made by a simple or 1 TCP session or 2 TCP session according to the implementation. As you can see, almost the resolvers are no compliance with this extension. It's so new. Also, we test the client subnet. This is the result for this extension. All of these resolvers are Chilean resolvers. You can see that it's not compared with the most common extensions. But the main idea is make that comparison between the DNS flag day and after the DNS flag day compliance and after the DNS flag day. This is a comparison of the minimal EDNS of the resolvers. We can see that the no error code increase in some of these servers. And I believe that is so important because most of the resolvers has a increase of, according to the draft that I told before. I believe that is better. Well, we can check here that almost 10,000 of the servers increased the no error code here in the chain query. The green line is the before the DNS flag day, and the dark line is the after the DNS flag day also. This is for the client subnet. And also, and to finally, is the server recognize the opcodes. This is a comparison before the DNS flag day and the after. Almost all the servers increase the number of the recognitions. And this is the classification for the algorithms at this stage. Almost all the resolvers has warnings to recognize the opcode and all the queries that we sent. And thanks. This is some of the tests in this repository, and this is my email. Thanks a lot.
Hi, it's Peter van Dijk at PowerDNS. 3 things. The first few slides, I see you testing with plus no rack. That might explain a big chunk of the refused you're seeing, which means you're not testing EDNS there, but testing that a resolver is not allowing you to snoop the cache.
Okay, yes.
Second, the queries you did after that, test the chain query and the subnet, etc. All the refused you see make me very sad.
Okay.
Third thing, I have a big stack of DNS Flag Day Survivor stickers for anybody that wants them. I'll be over there.
Okay, thank you.
John Reed, Akamai. I noticed early on in the slide, for example, you identified various resolver versions to the extent that they answered. Was there any further breakdown you could do of correlating this type of behavior either with specific resolver vendors or with specific other cohorts that might appear, such as consumer ISPs, business ISPs, things, any further correlation or breakdown you can do with that?
Yeah, we get some information based on this, but I show some raw results here. We recover all the resolvers by ASN or by some kind of version. We get some information, basic information about that, but we treat all in the same group. We don't split the test here.
Okay. Are there raw data available there or anywhere else?
Yeah.
Okay.
Yeah.
Cool. Thanks.
I think.
Hi, Tail. One thing about the refused answers also, unfortunately, the DNS is kind of overloaded what the meaning of refused is. And like in the case of client subnet, it was originally specified to specifically say, we're not going to do client subnet with you, but feel free to come back with a non-client subnet query, which is a real downside of the way ECS is implemented. But there's a lot you really can't tell about refused as currently given. And on a similar note, I don't think, and somebody might correct me, but I don't think any of the major resolver vendors currently implement chain query. It's been passed as an RFC, but actually doesn't have working code out there. And then I had one final remark. Oh, Mark Andrews. Have you looked at Mark Andrews' work on testing also EDNS compliance?
Okay, thanks. Yeah. Thank you. I'm going to do contact.
Okay, thank you very much,
Thank
Jason.
you very much.
Maybe bring an update to the mailing list or come back at some point if you have updated data.
Yeah, I have the. I don't have in the repository yet, but if you want to, you can touch it with me, and I can send the update.
You can also use our mailing list if you want to, provide some more information. So thank you.
Okay, thank you, Mira.
Okay, next is Runar. For 2 presentations, actually, we start with DiffServ.
Myself, Runa Barik from University of Oslo. I'll be presenting about how the DSCP impact on latency due to and using the thread plot box tool. Next. Okay. So here we see that WebRTC would like to use the DSCP code points, and we need to know whether it will work or not. First, we need to investigate whether the DSCP code point survives in the internet. So these previous studies. Okay, so the previous study shows that yes, the DSCP code point survives in the internet most often. So to do the test, we use the code points CS1, F42, and EF. So here is the plot box. So our hypothesis is the DSCP supporting routers. The DSCP supporting routers. Okay, sorry. The DSCP supporting routers would have impact on the latency during congestion. So first we need to create congestion on the internet path. So before that, we need to measure how many hops the DSCP code point survives. So here it is H. So we need to measure that first. After that, we send a probe packet. We send a set of UDP packets, larger size packets, with a CS0, and we set the TTL H+2, and all the packet will be destined to that. It will never end up in the destination IP address. So we'll not get any complaint, that will be fine. Then the next, after this probe, we send a set of monitoring packets. Those monitoring packets take, they are TTL limited, and they take CS0 and other DSCP code point, and all at once. So such that we can see the impact. Then we follow the procedure a few times to create enough congestion and consistent result. So let me tell you how this works here, how we get the impact if the router support DSCP code points. So let us say the router R1 and R2, when these TTL limited packets will reach R1, they will fire the TTL, so they will generate time exceeded messages. So same thing goes for router R2. Then using this formula, like basically what we are doing is that so we are sending UDP packets with a code point or CS0, and in return we are getting ICMP time exceeded message, and we are computing the RTT from that. And we take the difference between the two terms and with respect to their code points with the base CS0, and we compute the link delay due to the DSCP code point. Okay, so to do a bigger large-scale internet measurements, so we took EC2 machines, 6 EC2 machines in different countries. Then we had 12 non-net nodes in different countries like China, Korea, Germany, and 9 in Norway. So these are our vantage points to run, and we have nearly 1 Gbps link speed provided. So to decide the destination, the targets, so we took 52,000 IP addresses and 1 IP per AS. These ASs mostly cover transit or access ASs, content providers, enterprise, and classified by the CAIDA. So from these 52,000 IPs, we run the plot box with respect to 10,000. We don't want to create enough congestion for a long time, so we randomly took 10,000 and we did the measurement. From this measurement, we got nearly 100,000 plus unique links, and 50,000 are non-links, because we can see that they are not consecutive. And with this measurement, we traverse 200,000 unique internet paths. Okay, let me tell you the bad thing what we see. So only 1% of the links what we see has a negative impact. That means they increase the delay due to the code points. And these lines, these are the, so okay, these are mostly cover that means it could be like those ASS where the links are present, they may not like your code point, so that's why they may have a negative impact. And we can differentiate because they're overlapping. But what is the good thing is we see 2% latency improvement. So, and it clearly shows that EF, so basically this is a distribution with more than 1 millisecond. And these links are the median delays. So what the distribution of EF, actually it shifts right. So according to the WebRTC draft, we can see also from these results that EF performs better than F42 and better than CS1. Next. So yes, then we focus more towards the EF links, EF improvement links. So what we see is that what we can see in nearly 30 to 40% of the links where we saw EF gives at least 1 millisecond improvement, but CS1 and F42 almost give 0 improvement. So yeah. Next. So after that, what we did is that these reactive links, then we studied their ASS, which ASS they belong to. So then we plotted the number of DSCP affecting links per ASS. What we can see is that at least 60% of the ASS, where at least they have only one DSCP reactive links, they improve the latency of, due to the code point EF. And we can see at least nearly 10%, top 10, at least 6 reactive links. Next. So then we studied different ASS and analyzed. So we classified these links as whether they are ingress link or egress link or in the network of that AS. So we mean ingress link means, so from another AS to that router, and the traffic comes, then that router connected to that link and it improves the latency. So that is the ingress link. Then egress, when both routers of the link belongs to different ASS. So what we see then, what we did is that then we classified and we see that, let us say, China net backbone, we see maximum number of EF reactive links. And the important point of this slide is to show that we can see even due to DSCP code points, we see an improvement of 54 milliseconds in globe telecom. And we can see, for example, China net backbone, we have 0 ingress improvement, but the rest we see some improvement in the latency. Next. So this result is recent, and the 1.5 years before we had another measurement using our platform, Pling platform, where we are trying to see, we observed their DSCP policy from different ASS. So there we observed that, so basically that's why we compared these results. What we see in that the previous results is that nearly level 3 has 40% remarking policy, and Telia 60%, Cogent almost all, it remarks the DSCP, and it happens at the ingress. There is a 0 in the egress and the in network, and in the broadnet nearly least remarking. And we can see, we can confirm and see that where the star mark represents where the DSCP policy we observed, and these are the latency improvement that we see. We can see in the Cogent, so we can see in the improvement in ingress, but not in the ingress and egress. And that is all about DSCP measurements. And what we can see is that yes, there is opportunistic benefit from the DSCP code points that WebRTC could get. Yes, thank you. And any question?
Jelinkova, I just not sure how you define links between ISS, because if 2 routers belong to different ISS and it's direct peering, you might see both routers having IP addresses from one of the IS, right? because they're using address space belonging to one of them to address that peering link. And you don't know if it's going to be the next IS or previous IS in the past.
Yes, we see some cases like that. So basically, I see the link that could be either from internet exchange points or...
Yeah, exchanges are different, yeah, but if two ISs just have a private peering, it's really hard to tell from my experience if it's this link number from address space of the IS number 1 or IS number 2. So you don't know if it's the last link within IS or the first link outside of it.
Okay.
Gori Fairhurst, quick question. You talked about CS0 on the first slide and then CS1 later. Did you do any other tests with CS0 default?
No, yes, CS0, so all the latency improvement is compared with respect to CS0.
So you get improvement from using CS1 over CS0?
Yes.
Okay.
So here,
that's fun. And
this one, yeah.
Maybe that's why we're defining an LA PHB. So that's an interesting data point. Thank you.
Thanks.
All right, so we're ready to switch to Runa's second presentation. So let's get that one. And we just got 13 minutes left in the session.
Okay. So I'll be talking about, so what I did, this is, the talk is all about different, can we use the native DSCP, native protocols. So, yeah. So here what we are doing is that we are studying HTTP, DCCP, UDP Lite, and we use their transport checksum to see how the NAT boxes, home NATs, react to them. And for HTTP, we use also VTag. So what we did is that we had a local test bed study, so of self-equipment test. Then we studied about how the net filter in the Linux, NAT functionality. Then we studied IPF, PF, and IPFW in FreeBSD for the NATing. Then what we learned from this study. So these devices we collected from different places in Norway, mostly in Oslo, from their home from the colleagues. So what we see is that these are different kinds of network vendors, and we check their versions of OS, like supporting Linux kernel from 2.4 to 4.4. Some NAT devices support ThreadX and VxWorks, and some devices contain OpenWRT. So here is the test measurements that we did. We tried to test with the UDP with a zero checksum, and DCCP, SCTP, UDP Lite with the unknown protocols. And in the right side, we have observations. So what we see is that UDP zero checksum remains zero checksum. There is no computation of checksum. So that is observation 1. We just mentioned them. Then another is observation can be some devices could do simply NATing, IP level NATing, no touching of transport layer, and or some did no NATing if they see unknown protocols. Some simply drop the protocol packet if they don't understand the protocol. So what we see is that UDP with the zero checksum remains intact. That's a good thing. VxWorks drops the new protocol packets. If you send HTTP packets, it will drop it. Jensen, Topcom, and some D-Link devices do no NATing if it is unknown protocol. And so HTTP is a success because it can get, it does not have to change in the transport layer. So it is simply does NATing. So that is a benefit for HTTP, but not for DCCP and UDP Lite who need to change the checksum in the transport layer. So here is the net filter in Linux. We started Linux version 3.18 in the TP-Link using OpenWRT. So what we see is that the NAT module in Linux, it has two components, contract proto X and NAT proto X. This is the design part of that. So X could be HTTP, DCCP, or UDP Lite. So the contract proto X, it is responsible for NATing and then transport header verification, but it can't update the transport layer, and it fails if there is a port collision. It does not know how to handle the transport layer, but it can decide the entry in the buffer. But NAT proto is responsible for changing the proto port mapping or updating the checksum. So what we see is that Linux supports HTTP, DCCP, and they work normally. DCCP and UDP, they work normally, but HTTP, there is a problem. So HTTP, it should not change the transport layer port number, but Linux NAT filter, it changes the port number if there is a collision. And there is another variable, that NF contract checksum, that is, by default, it is 0. And it checks the checksum for incoming packets. So let us say UDP with the wrong checksum, and if this variable is enabled, maybe the packet will be dropped in there by the NAT box. So, but the good thing is that it is by default 0 because it needs extra computation, so nobody wants to enable it maybe. So the next thing is we studied FreeBSD, and in FreeBSD we 11.2, and we studied these firewalls. And we see that there is no support for DCCP and UDP Lite in the NAT module. Only IPFW and LIB alias supports HTTP implementation. So what we see in the previous implementation, UDP with so what we tried is that, so the multiple clients try to use the same NAT and observe their behavior. So for example, UDP with the 0 checksum, we see for all firewalls, the same behavior. So UDP 0 checksum remains intact. That is a good thing. The second is DCCP and UDP Lite. So something a little bit wrong is happening, like in IPFW, it handles like it does for the later clients. In the IPFW does like nothing. But there is a star which says that the packet will be forwarded to the last client. So that means when two clients are trying to use a DCCP protocol, so the first will succeed. The second, when the packet comes, it will override the. It will override. So once it will override, when the response for the first packet, let us say, luckily comes back, then it will give to the second client, later client, because the entry has been updated. So it is a bad thing. So these are different anomalies that we see in DCCP, or if it is unknown protocol, the way it handles. But HTTP, that is a good thing that it works well. Both two clients will succeed, and it updates basically VTag. It does not change the port number. So we can use actual HTTP NAT module for the HTTP deployment, like any NAT supporting HTTP. So we can use HTTP. So coming to the point that we observe that IP level HTTP is IP level NATing, so it can work at least for one client. It will work, but for new clients it will create a problem. So to see that those devices we had, we did a simple measurement to find the idle time, how much time the new client has to wait for a succeed in connection if the first client is not active. So what we see is that at least some of the devices give a smaller, for example, less than 200 seconds. Some are giving like normally most of the device give 10 minutes, which is a bad thing, but at least this is the current scenario that we see from these NAT devices. And what we learned from this measurement studies, that configuring the device, so basically configuring supporting the device, setting the checksum verification or new protocol. So what it means is that if you're using if you're using option, TCP option, that is better than using some other mechanism or new protocol. So better to use options rather than new protocol. So then emulating UDP Lite, we can emulate UDP with a 0 checksum for UDP Lite. So basically what we can do is that in the UDP we can put 0 checksum, and the application header can put the checksum. So we can handle that. So then native protocols are not by default. So it is good to support because most of the protocol DCCP and people, IETF is more interested in deploying these things. So it is, they are not deployed, but not enabled in the devices. So it is better to enable them. And then the pseudo header is a bad thing because it has a dependency over the IP layer. So better to remove, not to consider the pseudo header. Then to support multi-homing, individual connections should look like a single home connection. So for example, SCTP, the Linux, the way it changes, it updates the port number. So then individual connection of the same association to different NATs can be considered independently. So it will be okay if the client and the server can handle both the sites correctly. So that is the thing we learned from this local measurement study and from the different NAT modules. Thank you.
Ian Sweat, Google. Easy question. On slide 8, what was the bottom value of that graph? It didn't look like it was 0 indexed. Slide 8.
Is this?
No, go for it. That one. Yes, you have 200 seconds, and then what is DL5 at?
Okay, these are the devices that I put in the first slide, and they are the timeout from there. Yeah.
So is that like 100 seconds or 40 or?
So one
what's
is
the timeout for DL5?
Okay.
What's the lowest value? The first.
Yeah, it could be 30 or 40, I think. Yeah, I think 30 second around.
Okay.
Yeah.
Thank you. That's very informative.
Yeah.
Gori Ferris, quick question on the checksum thing. I quite like pseudo-header checksums. Did you try the CCO trick that was presented in Maprg before to see if that helped your checksum traversal? Huge echo, sorry.
So I did not test the CCO things, but it shows that if the system, that if I saw, sorry. Yeah, this variable, I think in your last presentation, last IETF, some devices that show that DSCP packets are dropping with bad checksum. Basically, this variable was enabled in those devices.
I'll talk offline. Thank you.
Okay, thank you very much, Runa. That makes it wrapping up just on time. Thank you for everybody who presented, brought data, and had discussion. We used to have another presentation that we tried to squeeze in at the agenda about quick migration, but this presentation already happened in Quick 2 days ago, I believe. So like we didn't want to cut out other presentations in that sense, but you can look at the recordings in the Quick meeting. The slides are also online on the Maprg agenda, and we put a link also in our wiki where we like note all the presentations so you have everything at once. So please do that. Cherie is also here if you have questions for her, if you want to stand up and show your face. So if you look at the slides in the recording, talk to her. Thank you, everybody. That's it. We will see each other in Montreal again. And most important, we will also have a hackathon table in Montreal again. So please join us there, bring data, and thank you. Yes.